Coulomb's law says that the force exerted by charge 1 on charge 2 is the product K Q1 Q2 over R12 squared multiplied by the vector R12 over R12. R12, not with the vector, is the magnitude of the vector R12. So this is the vector R12, here's the magnitude of R12, here's the magnitude of R12. Many times, of course, people will multiply this R12 by this R12 and express this as K Q1 Q2 times the R12 vector divided by R12 cubed. I want to emphasize that what we're doing is we're calculating the magnitude of the force and multiplying it by the unit vector R12 over magnitude of R12. So I want to write it like this. It's the way I'm almost always going to write it. If you just want to get the right answer with a calculation, then write it the other way. Or if you know exactly why the expression is what it is with the R12 cubed there, knowing that one of those R12s is what you divide into this to get a unit vector and that the rest is the magnitude of the vector, then go ahead and write it that way, but usually that form of the law obscures the heck out of what is really meant. Okay, and for 99% of the students, it obscures everything. Don't like it. If you disagree, that's all right. Okay, picture, here's Q1, here's Q2. The vector R12, which I haven't defined, is the vector from the position of Q1 to the position of Q2. Another thing I haven't said is that Q1 and Q2 can be are charge distributions that can be regarded as point charges. No dimensions. They aren't spread out in space. They exist purely at a point. And many types of charges can be treated as point charges. If you have a uniform spherical distribution of charge, as we can see very easily in a minute, as long as the spheres don't overlap, this still works, where this position is the center of the first sphere, this position is the center of the other. Now, if the charge distribution on the spheres is not uniform, you can't do that. Okay, the electric field is then defined in terms of force easily enough. Electric field is what you multiply by charge to get the force on it. And you get the electric field of the charge Q at some position x, y, z. The electric field at x, y, z due to charge Q is just this, K Q over R squared, which is a whole lot like this, but you only have the one charge Q, multiplied by the R vector divided by R, where now the R vector is the vector from the position of Q to the point x, y, z where you're calculating the field. Now it should be obvious then that if you throw a charge, say Q2, into this point, if you put a charge Q2 here, then if you multiply this by the electric field, you get a K times Q, Q2 over R squared, times an R vector that goes from Q to the Q2 divided by the magnitude of that vector. And except that we're using Q here where we use Q1 here, this is identical to this. So if you multiply Q2 by the electric field at x, y, z, you get the force exerted by this charge on charge Q2 at that point x, y, z. You regard Q as the source of the field. You regard the field as being a field through space. In other words, at every point of space you have x, y, z coordinates, and the field can be evaluated at that point. Okay, enough of that. You've been using electric fields. This is a review. But that's what electric field means, and everything else follows from that. If you have a charge distribution, rho of x, y, z, rho being the charge density, the density of charge per unit volume, the amount of charge per unit volume at that point. Then if we have some charge distribution here, we're rho of x, y, z again, at any point x, y, z within this cloud of charge or whatever it is. If the density at every point x, y, z within that cloud is rho of x, y, z, then we can, at least theoretically, calculate the electric field at point x naught, y naught, z naught that's not in that cloud. Okay? Now we could actually, do it within the cloud, but that gets a little tricky. There's some assumptions you have to make. So let's just assume that x naught, y naught, z naught is somewhere outside of that charge distribution. Well, here you've got something that might represent the charge distribution. It might be a charge over some wavy plane region in space. And, these little contour lines, whatever they are, divide that region up into little pieces, okay? Or this could represent a volume distribution, and these two-dimensional areas divided by these lines really kind of represent three-dimensional areas within the region. It doesn't really matter which, you just set it up as appropriate to the situation. We have, but I'm going to do this in terms of volume increments, so I'm going to assume that these are all volume increments, okay? And the picture is really a two-dimensional picture representing three-dimensional volumes. And you don't need to worry too much about that, because if you have a given volume region and you have multivariable calculus skills, you'll be able to figuratively or essentially divide that region up into small volume increments. So we're going to regard this as a typical volume increment with a volume delta V sub I. And we're going to say that this point here is your sample point. Now this point could be anywhere within the region, because as you know, when we take limits, shrink the regions down to zero so that we can get integrals, it doesn't really matter where we put the sample points. The region's going to shrink down so much that we don't really have much choice. And there isn't a whole lot of difference in the different points where we could put the sample points. Anyhow, they're confined to smaller and smaller regions, so where they are in the region becomes less and less important. So this is a typical region delta V sub I with a sample point xi star, yi star, zi star. Then I'll just digress. Of course, we could do this in cylindrical or spherical coordinates, etc., if you know about that. We might use a different coordinate system depending on the symmetries involved. In any case, again, we have a volume region with sample point xi star, yi star, zi star. So the field contribution at this point from this region will be regarded as what? Well, it'll be regarded as the field due to charge density times volume, where density is the density evaluated, the density function, our rho of x, y, z function, evaluated at our sample point xi star, yi star, zi star. And delta Vi is the volume of this region. And of course then the electric field is going to be K times the charge enclosed divided by the R squared multiplied by R over the R vector over the magnitude of R, where I use the subscript I, Q sub I, R sub I, vector R sub I, because this is a region delta V sub I. It's the ith region. Okay, so we use the I to indicate the charge in the ith region, the Ri to indicate the distance from our sample point of the ith region to whatever point x, y, z, or x naught, y naught, z naught, whatever it is, at which we're trying to calculate the electric field. So the delta E sub I, the contribution to the electric field, and the delta E sub I is a vector, so I should have had an arrow over it. Okay? I mean, I need to have an arrow over it since I've got an arrow over the R sub I, right? The delta E sub I then is just this calculation. And the only difference between this step and this step is, instead of Q sub I, I've written the way you calculate the Q sub I, density at the sample point multiplied by the volume increment. And a note here, the charge in the region is approximately Q sub I equals rho of xi star yi star zi star times delta v sub I. Now, I'm not going to go into any more detail and do examples. We've done examples, but this is an overview of how you think about the field due to a charge distribution.